We have already discussed these rates of change, velocity, acceleration, in describing motions of objects. Just like that, some derivatives also occur in economics. And just like these special words that we use in mechanics, velocity, acceleration, there are some special names given by economists to the rates that occur there in economic situations. And these are called marginal rates. Suppose you are in a manufacturing operation and you are manufacturing X tons of steel per week, and the cost of producing these X tons of steel per week is, say, C of X dollars. It depends on X. If X changes, the cost also changes. Now, if you want to produce more, say you produce X plus H tons per week, then the cost will also be more. The cost will be C of X plus H dollars. Now, the extra cost of producing this extra H tons obviously is going to be this difference. Now, if you divide this difference by H, then that is your average rate of increase in cost per ton per week. I mean, you can write like this also. Okay, so this is the average rate in which cost increases per ton per week. And if one now calculates the limit of this ratio as H approaches 0, then one gets the derivative. That derivative is called the marginal cost. That is this derivative. Is the marginal cost of producing one more unit. One more unit means in this case of producing one more ton of steel per week. Now, you can of course see what it means geometrically here. This curve is the graph of your cost function, y equals C of x. X is in tons per week and y in dollars. So, at this level of production x, actually I should have written this also. This is the marginal cost of producing one more unit per week when the current level of production is X tons per week. If X changes, possibly means most likely this limit will also change. So that is why at that level of production, the marginal cost is this. So at that level of production, the marginal cost is here, C of X. The cost of producing that much is C of X, and the marginal cost is the derivative. That means it's the slope of this curve or the slope of the tangent at this point. If you produce more X plus H tons per week, then the cost is more, C of X plus H. Now sometimes, of course, we define the marginal cost more loosely as the cost of producing one more unit. That is, instead of this derivative, you have this difference quotient, which is the cost of production of one more unit. This of course is not equal to this, but it's approximately equal to this. And that situation you can see here. Same thing, same diagram. So your level of production is X here. You have the cost of that much production, C of X here. Same thing, you also have the tangent at that point to the graph of y equal to C of X. But now if your level is X plus 1, the cost is more. This much is the cost, C of X plus 1. So by definition, the dC dx, your marginal cost at the level of production X, is the slope of this tangent. Now if you extend this vertical line to join the tangent there, then what will be the slope of the tangent? This length divided by this length, because you have this right angled triangle. However, this length is 1. So that just becomes this length. So this length is your dC dx. Whereas your average, this thing, it is an average. The average increase in production, average rate of increase in production when you produce one more unit is this. And that is the slope of this secant line joined by these 2 points on this curve. And that slope is like that one, this length divided by 1. But this length is the increase in cost for producing one more unit. So that's why we say that sometimes we define the marginal cost as the extra cost of producing one more unit. This approximates this well for large values of X. In principle, that's how things go. Okay, not for small values of X. When X is quite large, there this more accurately approximates the actual marginal cost. Let us now see an example. We don't need these diagrams anymore. Example 7. In this example, let me first take it down. So this is about marginal cost. Suppose it costs this much. C of x, which is x cubed minus 6x square plus 15x dollars to produce x radiators and where x lies between 8 and 30, when 8 to 30 radiators are produced. Within that range of production, the cost of producing X radiators is given by this formula. So the formula works only within that range. If your production is less than 8 radiators or more than 30, then most likely this formula does not really give you the cost very well. Okay. Now, say your shop currently produces 10 radiators. About how much extra will it cost to produce one more radiator a day? So that means you just have to calculate the marginal cost when your level of production is 10. Which means you have to differentiate this function with respect to x. That is, you have to first of all find the derivative. By the differentiation rules, we find the derivative to be this. And then to find the marginal cost at this level of production, you calculate this. Okay, and it comes out to be 195. So it will cost $195 to produce one more radiator per day if your shop currently produces 10 radiators. That means if it keeps on producing 11 radiators, say starting from some day, then this much will be the extra cost. That is the marginal cost. The next example is at first a little confusing. Let me write the actual language. Okay, I also got confused. This is marginal tax rate. Say your marginal income tax rate is 28% and your income, for some reason, say you got promoted in your job or something happened, increased by $1,000. Okay, so your income increases by $1,000. Then you may, this is the actual line in fact the authors use, you may expect to have to pay an extra $280 in income taxes. In taxes, that means on your income. The question is how and what is going on. The authors go on and say something more. It does not mean that you pay 28% of your income in taxes. It just means that you pay $0.28 out of every extra dollar you earn in taxes. Okay, so that's the situation. Your marginal income tax rate is 28% and your income increases for some reason by $1,000. Then you have to pay whatever you were already paying as taxes. On top of that, you have to pay an extra $280 in taxes. The marginal rate being 28% doesn't just simply mean that say you earn X dollars, 28% of X dollars is what you have to pay in taxes. No. It means that for every extra dollar that you earn, when your income increases, for every extra dollar you have to pay this much to the government in income taxes. But why? What is going on here? See, this rate is this because it's marginal rate. So it is DTDI. Say T is the your tax if your income is I, both in dollars. This is 28% or 0.28. This means that if your income, say whatever your original income was, it was I dollars, gets increased by 1000, then this is your difference quotient, that is approximately equal to this derivative. Just like how we loosely define that marginal rate as marginal cost as the cost of producing one more unit, this quantity, which is itself is not a derivative, it approximately equals dt di. That means this is this. So what does it mean ultimately? This is approximately equal to T of I plus 0.28 times 1000, or T of I plus 280. So that is why on top of your original tax that you used to pay when your earning was I dollars, you have to pay this extra $280 as your tax now that your income has increased. Which means that if you again divide this by 1000, because your income increased by $1000, so if you divide this quantity, only this one, 280 by 1000, then that is the extra tax that you pay for every extra dollar that you are earning. Okay, so that's what is going on here. And finally, there is one more which involves income, not paying someone but earning something. So this is marginal revenue. This is not example 9 though. I mean, just now we have seen example 9, right? Or did we see example? Oh, okay. This is example 8. I think I incorrectly wrote it as example 9. Now only example 9 comes. Sorry about that. Marginal revenue. I won't write everything down, okay? Suppose that you are selling candy bars, and for every X thousand candy bars, that you sell, the revenue that this sale generates is given by this formula: x cube minus 3x square plus 12x, provided the sales remains in this range. Within this range only this formula works. then the marginal revenue, just like the marginal cost is mathematically the derivative. Okay. What does it measure? It measures how much you will earn extra if your sales go up by 1 unit. That's what it measures at that level of sale X. If X changes, then it will also change. For example, if you are currently selling 10,000 candy bars, then your marginal revenue at that level of sale will be $252. This means that if you increase your sale from 10,000 candy bars to one more unit, not 10,001 candy bars. Here the unit itself is 1000 candy bars. That means from 10,000 if you go to 11,000 and if you sell all those things, then the revenue will increase by this much. Okay. And in one exercise problem, we have a very peculiar to me situation where say you keep on increasing more and more the sale, what will happen to this marginal revenue? It actually decreases. Okay, that's a little counterintuitive, but it is what it is. Now you may have noticed one last thing, that these costs and revenues are being expressed as polynomials in the variable x, whatever that represents. That is, it may represent sale or it may represent the level of production, whatever it is representing actually. Why only polynomials? See, just like the sciences, economics also deals with real life situations. And when you deal with real life situations, things are extremely complicated. Things are so complicated that you have to make some compromise. You cannot take everything into account that is influencing whatever you are studying. If you study something in real life, many things are influencing from all sides that thing. Now, you cannot possibly take into account all those influences. If you try to do so, the theory or the equations, inequalities, whatever you may end up having, will itself be extremely complicated, so complicated that it will be useless because you won't be able to use it due to its complexity. So the compromise you have to make is that you have to neglect some influences which are not really that important. So the equations you end up having, they do not represent the exact reality. In reality, there is no exactness. Instead, you get an approximate something, some equation. Even then, it is very useful. So, theories in economics, just like we have theories in the sciences, for example, in physics you have the theory of relativity, quantum mechanics, just like that, economists have studied and they came up with many theories. Those theories suggest that this type of functions are enough in most situations to quite accurately capture what's going on, how much cost we will have. And that's why you see there is a range of applicability. If things become really very extreme, then these functions do not work. but within these ranges of applicability that we get from theories of economics, these functions work reasonably well. Polynomials are already very easy to work with for many reasons. They are continuous everywhere, they are differentiable everywhere, they are integrable because they are continuous. So they can be used very nicely. Now you may also notice that we have cubic polynomials. For some reason, the economists will know, cubic polynomials capture things nicely, but at the same time they are not too complicated. Because you have a cubic polynomial, you can you can use its simplicity, mathematical simplicity, to do things like this quite quickly. But at the same time, it's not so simple that it won't be able to capture the actual thing. So that is why polynomials are the things that we see mostly in this type of things in economics. And with this thing, this section ends. And after that, of course, we have our usual dreaded exercises. So we will cut down the exercise amount in half coming from the next month. I will solve only the even ones, and there also I won't solve everything. If I see similar exercises, I will just leave those things to you. Our plan is to speed things up really very much. So let's see how that happens. And tomorrow, as usual, according to our schedule, we have linear algebra. And I think 2 more exercise problems are still there in that section where we are right now. So tomorrow we will solve those 2, and then we will go to the next section, which involves rational canonical forms. So that's just it for tonight. See you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.